Okay, as of now, we have been using these notation interchangeably. However, what I'd really like to show is that this can be split such as we get this top equation here. And let's interpret the meaning of this. Well, first of all, dy over dx tells me my derivative, which is the rate of change of y with respect to x, but on my top equation, all I'm talking about is how fast y is changing at any given instant of x value plus how fast x is changing at any given instant. So let me give you an example of this. So let's say we had a function of y equals the sine of x squared. So if I was to use, uh, so technically there are two ways you can visualize this. I kind of just like to visualize taking the derivative where I end up with dy dx equals the cosine of x squared times 2x using the chain rule. And if I want to find the instantaneous change of y, I simply multiply both sides. So and that is my differential of the function y equals sine of x squared. So I'm going to dig in a little bit deeper into what dy and dx are and how we can utilize them. So basically, my dy and dx's represent changes in value of y and changes in value of x. So what I'm going to do is bring in a graph of Desmos here for just a second, and we're going to look at that function y equals sine of x that we had, and I'm going to look at these 2 points here. So these points are labeled on my graph, and we're going to talk about what's happening in between these 2 points. So let me take this picture so that I can write on it and get a visual here. Okay. So there's my graph. Okay. So let's talk about dy. So basically, what I want you, hang on a second, I'm going to make this small, small, and then big again. Okay. Now, get my pen out. Between here and here, these components you should recognize as my rise, which is dy, and my run, delta y and delta x. Now, delta x we're going to use as dx as well for the purpose of what we're examining here. And what I'm really interested in is dy. So, dy versus delta y. Now, delta y is very easy to calculate. It's just simply y2 minus y1. And we have those numbers. Y2 is 0.841 minus y1, which is 0.247. Let me grab my calculator. And we get delta y is 0.594. Now, what dy should represent? Let me draw this here. And what I'm really interested in, and it should be close, but not necessarily the same. So I'm just drawing, if you will, the best tangent line I can visually at my point. And along that tangent line, if I was to move over, and of course this delta x here, let's talk about the delta x for just 1 second. Delta, x, we're going from 0.5 to 1, so delta x, of course, is x2 minus x1, which is 0.5. So when I move over half a unit in the x direction, on the actual function, the y value goes up by 0.594. However, if I was on that tangent, this, I'm going to erase it here, would be how fast, so dy is the rate at which y is changing on my tangent. And so with that, we would want to plug that into the formula. I'm going to use a scientific calculator here. So, and we can see that. Let me get one up. And I'm going to enter it where on another screen I'll bring it in so you can see it. So what we have is the cosine of x, and in this case, what we're really talking about is at this starting point here. So my x value, and here's what I'm putting in here. I'm doing this calculation. Sorry about that. Let's see. Oops. Oh, it doesn't want to write on that. So I'm putting in cosine at that x value of 0.5 squared times 2 times that 0.5, and dx and delta x I'm going to use interchangeably, and that will be times 0.5. And this is the dy I should get. And dy visually looks like it's definitely going to be smaller than this number along that tangent line. So when I plug that in, point, oops, up here, 0.5 squared times 2 times 0.5 times 0.5. I should be getting a number slightly smaller than 0.594, and that's exactly what we get here. So this is what I get my scientific calculator when I plug it, which is what I would be expecting to get, a number smaller and that was my dy. So notice, as I'm moving along the function instantaneously at x equals 0.5, if x is going to increase from 0.5 to 0.1 and I was to remain basically on that tangent line, then my y value would increase by 0.8445 approximately, larger than it was to begin with. Hopefully that makes sense.